September the 23rd, 1999. Mission Control falls quiet. Not the quiet of triumph, but the quiet of absence. For 4 years, engineers had drawn its path across the void. For 10 months, it had fallen silently through interplanetary dark, threading a needle of trajectory across 200 million kilometers of nothing. The Mars Climate Orbiter, humanity's first interplanetary weather satellite, was meant to unveil the red planet's atmosphere, to map water's hidden distribution across an alien world. It carried with it the calculations of brilliant minds, the funding of a nation, the hope of a discipline. Then, as it reached for orbit, the signal vanished. No warning, no telemetry, just static where data should have sung. More than $300 million gone in an instant, swallowed by the dark it had only moments before been navigating. Investigators spent weeks combing through the wreckage of data, until November the 11th revealed a truth almost too mundane for so cosmic a failure: a miscommunication of units. NASA had calculated in the metric language of kilograms and meters. A contractor, working the same numbers, had read them as pounds and feet. A satellite was lost not to the violence of the cosmos, but to the fragility of human agreement. Here is the lesson written in the wreckage of a spacecraft. The modern scientific world is built on standardization, and without it, chaos does not merely threaten, it consumes. And yet examine our units closely, and a strange truth emerges. They are not universal at all. They are parochial. An inch is the breadth of a man's thumb. A kilogram echoes the mass of a liter of water drawn from Earth's rivers. An hour is nothing more than a slice of one planet's spin, carved arbitrarily into 24 pieces. These are measures born of flesh and home, useful here, meaningless elsewhere. For somewhere past the orbit of Neptune, there is no thumb to measure breadth, no water to weigh, no single planetary rotation to call a day. The cosmos keeps no calendar in our image. So a question arose, quiet but immense. How might an extraterrestrial intelligence quantify its world? And more urgently, how might we quantify the universe itself, stripped of every human bias, every earthly accident of scale? This was the riddle that consumed Max Planck in the final years of the 19th century. The German physicist, a professor at the Friedrich Wilhelm University in Berlin, would go on to earn the Nobel Prize. But in these years, he was simply a man staring into the architecture of physical law, searching for something that did not bend with circumstance. Planets raced around their stars at wildly different speeds. Gravity pulled differently on a moon than on its parent world. Nothing in the visible cosmos seemed fixed. But beneath the variation, Planck saw bedrock. The speed of light, the gravitational constant. Quantities that did not waver, not on Earth, not on Mars, not at the edge of observable space. These were the cosmos's own fingerprints, etched into the fabric of space-time itself, indifferent to whoever might be watching. By mathematically forcing these constants to equal 1, Planck discovered he could derive units belonging not to any culture or planet, but to the universe itself. In 1899, he revealed his calculations. The Planck length, 1.6 times 10 to the power of Niederth meters. A decillionth of a millimeter, a span so small it borders on the inconceivable. Planck time, derived by dividing that already vanishing length by the staggering speed of light, proved smaller still, 5.4 times 10 to the power of -4 seconds. Let that settle. There are more units of Planck time within a single second than seconds that have ever elapsed since the dawn of the universe. For a century, these numbers seemed almost a curiosity, too small for intuition, too abstract for application. But at the frontier of cosmology, they have become indispensable. Observation after observation has lent overwhelming weight to a theory once dismissed as outlandish, that the entire universe erupted into being some 13.8 billion years ago, expanding from an infinitesimal point in a violent exponential bloom, the Big Bang. Cosmologists have pressed backward through that explosive history, reconstructing the universe's earliest behavior with a precision that would have seemed impossible a century ago, narrowing the unknown to within a sliver of a single second after creation itself. And it is here, at this furthest edge of knowledge, that Planck's units finally come into their own. For physicists now ask the boldest question imaginable. What happened when the universe itself was only 1 Planck length wide, when its entire existence had lasted only a single unit of Planck time? This moment has a name, the Planck era. It is the final frontier of Big Bang cosmology, a lawless and untamed wilderness where the familiar laws of physics, so reliable across billions of years and trillions of kilometers, simply collapse beneath the unimaginable pressure of a cosmos compressed into almost nothing. In that first sliver of existence, the rules dissolve, and in their place rises a realm of staggering, mind-bending possibility, the true beginning of everything we are still struggling to understand. For 3 centuries, the universe obeyed a single elegant whisper. In the closing years of the 17th century, Isaac Newton set down his Principia Mathematica, and within its pages he offered humanity a key to the heavens, 3 laws of motion, and beside them, the universal law of gravitation. With breathtaking simplicity, he bound the falling apple and the wheeling moon into a single equation, force proportional to the masses of 2 bodies, divided by the square of the distance between them. It was a law of such crystalline clarity that for more than 200 years it described every orbit, every tide, every plummeting stone, with a precision that seemed to brook no argument. Newton had not merely measured the cosmos, he had, it seemed, explained it. But laws that seem eternal are sometimes only patient. In Bern, Switzerland, in a dim patent office, a young man watched the clock drag through the final hour of his shift. He was no celebrated scholar. He had stumbled through school carrying a reputation for insolence, had failed to secure a teaching post, and had settled, reluctantly, into examining other men's inventions. Yet in the margins of his patent applications, small diagrams crept in, sketches of imagined systems, fragments of a mind that lived elsewhere, in notebooks crowded with equations no one had asked him to write. His name was Albert Einstein, and though the world had not yet noticed, his thoughts were already racing toward the edge of what was known. In 1905, that quiet rebellion broke into the open. Einstein discarded the comfortable certainties of classical mechanics and proposed something stranger, a theory describing how matter and light behave as they approach the very speed of light itself. He called it special relativity. When his papers reached the desk of Max Planck, the patent clerk's exile ended. Physics had found him at last. Yet special relativity was only a beginning. For the next 10 years, Einstein wrestled with a deeper problem: how to reconcile gravity itself with this new vision of space and time. Newton's law still towered over physics, explaining nearly everything observed in the heavens. To challenge it required not correction, but reinvention. Einstein did not relent. From that decade of struggle emerged general relativity, mathematics of staggering complexity, describing a universe far stranger than Newton had ever imagined. Spacetime, in this new vision, is not a passive stage. It is fabric, living, responsive, malleable. Every mass presses a curve into it. The greater the mass, the deeper the well. A star does not simply attract its planets across empty distance, it carves a basin in the geometry of existence itself, and the planets endlessly trace its curved rim, prisoners of geometry rather than force. The universe confirmed it. Mercury's orbit, which had defied Newtonian prediction for decades, fell perfectly into place beneath Einstein's equations. A new architecture of gravity had arrived, sharper, deeper, and more faithful to nature than anything that came before. And within this new mathematics, the priest-physicist Georges Lemaitre found something extraordinary, a solution describing a universe expanding outward from an unimaginably hot, dense beginning. It was the first seed of what would grow into the Big Bang theory. But every framework, however magnificent, has its breaking point. Deep within black holes, objects whose mass can swell to 100 billion times that of our Sun, all crushed into a single dimensionless point, space-time curves so violently that not even light can claw its way free. Here, at last, Einstein's exquisite equations falter. They speak of infinite density, infinite curvature, a singularity beyond calculation. And mathematics, however powerful, recoils from infinity. This is the threshold where the story turns. For that same impossible density, hiding at the heart of every black hole, bears an uncanny resemblance to the condition of the infant universe itself, to the so-called Planck era. For a fraction of a second, the entire mass of the cosmos was compressed into a volume 100 billion times smaller than a single proton. General relativity can chart the slow grandeur of galaxies, the patient orbits of stars, the bending of starlight around distant suns. But it falls silent at the very beginning. It cannot speak to that first searing instant when the universe was smaller than imagination and hotter than language can describe. To understand that moment, scientists would have to look beyond Einstein into a deeper, stranger mystery still waiting to be solved.